to the next talk, which is Idealness of K-wise intersecting families. This is work by Ahmad, Abdi, Gerard Cornejols, Tony Wynn, and Dabin Lee, and the speaker will be
Ahmad Abdi.
Ahmad Abdi.
Yes. So I'm going to share my screen. Okay. Thank you, Michele, for chairing the session. Thank you to all the PC members, and especially to Dan Beanstalk, as well as to the rest of the organizers. So as Michele mentioned, I'm going to talk about idealness of K-wise intersecting families. Yes, this is joint work with Gerard Cornejols, Tony Hyun, and Dabin Lee. All right. So this is how I start every single one of my talks. I start by defining what a clutter is. So let B be a finite set of elements, and let curly C be a family of subsets of V, which I'll refer to as members. I'll say that the family C is a clutter over ground set V if no member contains another one. These are also referred to as Sperner families and also anti-chains. But in polyhedral combinatorics, we usually refer to them as clutters, following Edmonds and Fulkerson. Okay. So I'll be working with clutters, and I'll get right to the problem. There's a big conjecture that we have, and it's a very simple conjecture, and it's very easy to state, yet we haven't been able to solve it. So I'm just gonna put it out there in case anybody can solve it. So I'll say that my clutter C is a K-wise intersecting clutter if every set of K members have a common element, but not all the members have a common element. Okay, so the reason I have the second condition is to eliminate stupid examples. I could have clutters where every member contains a fixed element, and obviously every subset of the members would intersect in that case. So yeah, so a more formal way to write this down is to just say the intersection of any K members or less is non-empty for all K members in C. Okay, but the intersection of all the members is it is empty. Sorry. Okay, and now I'm ready to state my our conjecture. The conjecture is that there is a constant K such that for every K-wise intersecting clutter over ground set V, the polyhedron that I have here has a fractional vertex. What is this polyhedron? First off, the polyhedron is in the non-negative orthant. It assigns a variable to every element of the clutter, every element in the ground set. And it will have a constraint per member. It'll have a constraint per member, and the constraint is a set covering constraint. It says that the sum of the variables in the member, in every member, is at least one. All right, so this is referred to as a set covering polyhedron. So this is referred to as a set covering polyhedron. All right. Is the conjecture clear? That's the main message of our paper. That's this conjecture. All right. So what does this paper do? This paper motivates at least partially the conjecture. There are motivations for this conjecture that we just simply didn't have enough of a space limit to talk about. I'll mention one of the motivations, and in the full journal, full version of the paper, we'll try to mention all the other motivations for the conjecture. It refutes the conjecture for k equals to 2 and 3. For k equals to 2, we're simply dealing with intersecting families, two-wise intersecting families, and this is fairly easy. But for k equals 3, the counterexample is not easy at all. And I'll explain that. We conjectured that it should be true for k equals to 4. We prove it for k equals to 4 for a special class of clutters called binary clutters. These are clutters that come from binary matroids, and I'll explain that. The paper shows that the k equals to 5 case follows from a very old conjecture of Seymour. It was in fact unpublished from 1975. It can be found in Scriver's 3-volume book in the further notes section. And it discusses some applications of our theorem. And the applications are to cycle covers in graphs, uniform cycle covers as well as dyadic fractional packings in clutters. I unfortunately won't have time to discuss all of this. So let me explain what this talk is going to discuss. So this talk will try to motivate the conjecture, again, at least partially. It'll refute the conjecture for k equals to 2 and 3, and I'll outline the proof for k equals to 4 for binary clutters. Okay. Before going further, the motivation I'm going to give for the conjecture, there's various motivations. One motivation in particular that we did not mention in the paper is from an algorithmic point of view. One point that was brought up by actually several of the referees for our paper was that this doesn't say anything about testing idealness. And in fact, that is the main motivation for this conjecture. If this conjecture were true, it would actually it would give a significant progress towards testing idealness of a special class of clutters called cuboids. That I would and cuboids, I'll talk about cuboids in this talk. So actually, it does have algorithmic. This conjecture would have algorithmic implications for testing idealness. And yeah, all right. So, are there any questions before I go further? Okay. All right. So I'm gonna discuss the motivation that we had in the paper. All right, and this motivation comes from the sets covering LPs. So given any clutter over ground set V, I can look at the corresponding set covering linear program, which tries to minimize the weight of a vector X subject to covering constraints, one for each member of the clutter, as well as non-negativity constraints. Okay, we may assume that the W we're given has only non-negative entries and also integral entries. That's without loss of generality. Okay, a particularly interesting class of linear programs is is those that form an ideal formulation or a perfect formulation. We'll say that the clutter C is ideal if this LP has an integral optimal solution for every non-negative positive, for every non-negative integral vector W. Okay. In other words, by using basic polyhedral theory, what we're saying here is that the feasible region that defines this linear program is an integral polyhedron that has no fractional vertex. Okay. Why are ideal clutters interesting? Ideal clutters are interesting because you could solve the set covering integer program in polynomial time. Okay, if I give you the whole clutter. Okay, because you could drop integrality constraints, the integrality constraints, and you would get this linear program, but this linear program only outputs integral solutions, so you're not losing anything. Okay. Now, if now we can rephrase our conjecture in terms of idealness. The conjecture says that there's an integer k such that every k-wise intersecting clutter is non-ideal. Okay. All right. Now, let's look at the dual of the set covering linear program that we had. So the dual will be a maximization problem. It'll be a packing problem with congestion constraints. We'll have non-negative variables y assigned to all the members subject to congestion constraints. For every element, we want the sum of the y sub c's, where c contains that element, to be at most w sub u. So we want the congestion of every element to be bounded from the above. And subject to these congestion constraints, we want to maximize the value of the solution y. This y is referred to as a fractional packing. So this is a fractional packing problem. Okay. Just like in the set covering case, in the primal case, we can impose integrality conditions here. We'll say that the clutter C is Mengerian if the dual has an integral optimal solution for every right-hand side vector W. Okay, so the notion of Mengerian is in bijection with the notion of total dual integrality for set covering problems. So I'll say the clutter C is Mengerian if the corresponding set covering program is total dual integral. Okay. Now there's a classical result of Edmonds and Giles that tells you that total dual integrality implies primal integrality. In the language of clutters, that says that if a clutter is Mengerian, then it is ideal. Okay, so if we look at these Mengerian clutters and look at weights equal to the all ones weight, then what is this program doing? It's looking for a minimum size subset of the elements that intersect every member at least once. So this is a hitting set problem, or it's a covering problem. All right, we're trying to come up with a minimum set of elements to intersect every member at least once. If you look at this problem, what is it doing? The congestions are now 1, the W's are 1, and we're assigning integral weights W here, because during the Mengerian case, we could just focus on integral Y. We're looking for a maximum size set of members that are pairwise disjoint. So this is just a packing problem. We're looking for a maximum number of pairwise disjoint members. Okay, so if you give me a Mengerian clutter, if you put these two things together, if you give me a Mengerian clutter, then the minimum number of elements needed to intersect every member, which is denoted by tau of C, is equal to the maximum number of pairwise disjoint members, which is denoted nu of C. All right, so Mengerian clutters are especially nice because they lead to min-maxed theorems. So if you look at that corollary, you'll see that two-wise intersecting clutters are not Mengerian. If you give me, I'll refer to two-wise intersecting clutters simply as intersecting clutters. For these clutters, the packing number will be 1 because we will not have disjoint members. Whereas the covering number is at least 2 because not all the members have a common element. So there's a gap between the covering number and the packing number. So these two-wise intersecting clutters are sort of the simplest family of clutters you could come up with that are not Mengerian. Now, I introduced two properties for clutters, idealness and Mengerian. I mentioned that Mengerian clutters are ideal due to the result of Edmonds and Giles. However, the converse is not true, and we'll see an example of that. And a key question that turns out to be very important for several open conjectures in the area, such as the replication conjecture and the tau equals 2 conjecture, is understanding the gap between idealness and Mengerian. So it's just understanding this, the difference here. And one interesting fact is that the important ideal non-Mengerian examples that you can come up with, the important ones that are known, are all intersecting clutters. So you could look at the class of intersecting clutters, and it would not intersect the Venn diagram. You can look at this Venn diagram. It would be the strength from Mengerian, but it does intersect the ideal set. And all the interesting examples are here. Okay, and so intersecting starts with two-wise intersecting, and you could now bump up the K, go from two-wise intersecting to K-wise intersecting, and you'll get a smaller and smaller class every time. And the conjecture is that after a certain point, it'll get so small that you'll be disjoint from idealness. All right, so there is an integer K such that there exists no ideal K-wise intersecting clutter. Again, so this conjecture tries to address the gap between idealness and Mengerian. And this is one motivation for our conjecture. All right, so what are our counterexamples for K equals to 2? So there's a classical one due to Lovas. Consider the clutter of triangles of K4. So my ground set is going to be the edges of K4, and the members will be the triangles as outlined there. Now K4 doesn't have disjoint triangles. So this clutter will be, this clutter will be intersecting. Okay, so it's K4 doesn't have disjoint triangles. However, it can be shown that it's an ideal clutter. This is I always leave it as an exercise for in my courses, but it's a terse exercise. But I'll show you a clean proof of this using the machinery we've developed. Okay, so that's one example of an ideal intersecting clutter. There's many other examples. In fact, there's hundreds of small minimal examples. By minimal, I mean with respect to a minor operation. And these small examples date back to Scriver and Kornijolskonen and Margot. I think together they came up with about 15 small examples, and recently together with Gerard, Natalie, and Devine, we came up with about 700 more small examples. By small, I mean the number of elements is at most 50. And not only that, there's 2 infinite classes of minimal examples. One infinite class was given by Kornijolskonen and Margot, and recently we came up with another infinite class. So it's a zoo. So there's many examples of ideal intersecting clutters. All right, so we need to modify our conjecture. They're saying that there exists an integer K greater than or equal to 3, because it's not true for K equals to 2. Okay, so the next question is, well, are there any ideal 3-wise intersecting clutters? I mean, all these examples that I gave you, is any of them 3-wise intersecting? The answer is no, none of them are. And in fact, we know of only one example. We know of only one example, one minimal example so far. And it's got 30 elements, just to tell you how large it is. And 30 is just the number of elements in the ground set. What is this? To tell you what this is, I need to tell you about cuboids. Okay, so let's take the discrete unit hypercube 0, 1 to the n. So this is an n-dimensional hypercube. I'm looking at the vertices. And let's take a subset of these vertices, S. The cuboid of S, denoted cuboid of S, is a clutter over the ground set 1 through 2n, whose members will be in correspondence with the points in S. And what is this correspondence? For every point in S, I'm gonna expand this point to a 2n dimensional point by appending 1 minus the point to it. So I'll first put the first coordinate of P and then 1 minus the coordinate, P to 1 minus the coordinate, P and 1 minus the coordinate. So this is what I'm being applied to with what 0 and 1. I've encoded all the twistings. So if you look at this example, I'll start with these 4 points in the 3-dimensional hypercube, 0, 0, 0, 1, 1, 0, etc. And what I'll do is I'll just fill in the gap. So 1 would go here, 1, 1, 0, 0, 1, etc. And then I'll interpret the first row as a member. So this is going to be 2, 4, 6. The next one is going to be 1, 3, 6, etc. And you could do the same for the other ones. And I've done that. Oh, I haven't done it here. All right. So you could do this 1, 0, 1, 0, 0. I changed the slides last minute. You could do this. So this is going to be 1, 4, 5. And this is going to be 2, 3, 5. And the cuboid turns out to be just the clutter Q6, the triangles of K4. So triangles of K4, which has ground set of size 6, comes from this 3-dimensional hypercube. Okay. And okay, so the question is, when is now? What I want to do is I want to understand what the conjecture is saying just for cuboids, for the class of cuboids. So first thing you want to understand is, what does the K-wise intersecting condition imply for cuboids? So so we want every K members to have a common intersection. That's going to imply that every K points in S have a common coordinate. So even a common 0 will lead to a common element because we're complementing these. However, we don't want all the members to have a common element. That's going to mean that not all the points have a common coordinate. Okay. All right, so that's idealness of that's K-wise intersecting cuboids. How about idealness? So there's this result that we proved a few years ago. A cuboid is an ideal clutter if and only if the subset of the hypercube you have is so-called cube ideal. And what is cube ideal? We'll say that a set is cube ideal if the convex hull can be described by generalized set covering inequalities. Okay, so what's happening is in the cuboid world, we have set covering inequalities in the 2n-dimensional space. But when we go back to the n-dimensional space, we don't see a difference between 0 and 1. So we need to be able to allow both xi and 1 minus xi. So we're looking so-called generalized set covering inequalities. And if you look at the set of 4 points that I showed to you, that's going to be a cube ideal set. Why? Because if you look at this, we're getting a simplex, and every facet is cutting off a single point. And if you cut off a single point, that means you're cutting off a subhypercube, and this is precisely what generalized set covering inequalities do. They cut off subhypercubes. So this is 1 minus x1, 1 minus x2, plus 1 minus x3 greater than or equal to. Okay. And the conjecture phrased in terms of cuboids tells you that whenever you give me a cubideal set, either all the points agree on a coordinate or there's a subset of at most k points that don't agree on a coordinate. All right, so I'm basically, here I've written the contrapositive of the conjecture for cuboids.
Ahmad?
Yes. Yes, I'm running out of time. Yes, yes. So, and what's very interesting is that these two conjectures are actually equivalent. It suffices to prove the conjecture just for cuboids. And this is quite interesting. It tells you that this class of clutters is very important. All right. And what we do is we prove this conjecture for k equals to 4 for binary spaces. Okay, binary spaces are just vector spaces over GF2. Now, I don't have time to talk about this, but this proof relies on 3 results. One ingredient is that cubideal binary spaces are in correspondence with binary matrices with the sums of circuits property. Another result is a classification theorem of Seymour, given a decomposition theorem for the sums of circuits property. And finally, the 8-flow theorem of JJ in graph theory. Now, in the I don't have time, but I was gonna tell you how 8-flow theorem JJ's result shows up in this context, but I don't have time, unfortunately. And the counterexample for k equals to 3, maybe I'll tell you that it comes from the Peterson. It comes from the Peterson. If you look at the Peterson graph, take its cycle space, whatever that means, I don't have time to tell you, and then move to the cuboid of that. It'll give you an ideal 3-wise intersecting clutter. And this clutter, although not defined this way, but defined in a completely different way, T30, was noticed by Seymour back in the 70s. But he wasn't looking at these 3-wise intersecting conditions. Actually, Scriver named it, Seymour named it T30s. All right. And we also prove it for a class of clutters called binary clutters. And that's done by reducing conjecture 1 to conjecture 2 for even for binary clutters, which is not obvious. Anyways, yeah, I didn't have time to go through any of this. Unfortunately, I was going too slowly. But yeah, the main message of the talk is basically this conjecture. I refuted it for k equals to 2 and k equals to 3, and I'm posing it out there for k equals to 4. We believe it's true for k equals to 4. All right, okay, thank you.
Thank you, Ahmad. And if you unmute yourself and applaud the speaker. Sam asks, what are you using the 8-flow theorem of Gégère?
Yeah, so basically, if you we use the 8-flow theorem of JJ to prove the conjecture for binary spaces. I think everything's summarized here. Where is it? Here. So if you look at the cubideal sets, the conjecture, we have this conjecture 2. It turns out that from every graph, you could construct a cubideal set S. And the cubideal set you get is constructed from the cycle space of the graph. Now, JJ's theorem tells you that every bridgeless graph has 3 cycles whose union is the H set. You take these 3 cycles and it somehow corresponds to 4 points in the cycle space that do not agree on a coordinate. So that's how it's used.
So I don't see any other questions.
I can
So,
ask a question.
yes.
It's okay. Let me try and start my video or not. Okay. Hey.
Hi, Dan.
Hi. So if you were going to, you know, in trying to prove this kind of conjecture, I mean, do you expect like, so you need to somehow find a fractional vertex? Do you expect it to be like exposed by something simple, like, you know, the all ones objective, or do you have to be very, you know, very fancy about it somehow?
That's a very good question. Actually, I think, yeah, the vector is not going to be the direction you'll go is not going to be obvious to find, because the direction you go is going to tell you what minor, what bad minor to look for.
Okay.
So because minor operations essentially correspond to setting the weights to 0 or infinity. So figuring out which direction to go is the same as figuring out which bad minor to look for in the clutter. So yeah, I mean, I did try to prove it for a simple objective function, but it's not true for any objective function you can come up with. I can probably come up with a counterexample.
So for the objective function of all ones, you can find for every k a k intersecting clutter, which has in which the optimum solution is integral for this objective function.
For specific examples, yes. So I think if you look at the prototypical example of K-wise intersecting clutters, it would be clutters where every member is super large. And I think for, I could probably come up with an example there, or even just cuboids, where the all ones vector just wouldn't do. I would have to, yeah.
So you are in trouble, Ahmad.
So we did prove something similar in the last IPCO. In the last IPCO, what we showed was that if a clutter and its blocker are both intersecting clutters, then you're non-ideal. And there in the proof, again, we don't know where the objective function, or what the objective function is. In fact, the proof used quadratic programming. Yeah. So sometimes you can prove non-idealness without even knowing where the fractional vertex is. Yeah. All right.
Any more questions? Dan, thanks again.
Thank you.